Hey guys, Mr. T here, just doing a quick video of the solutions for your practice advanced chemistry test. Doing this live, no preparation, so hopefully I don't stuff anything up, but also it'll give you a good idea of the speed that you should work at. We tend to write tests with the idea of 1 mark per minute, plus a little bit of extra time for you considering you're a student, and also to go back and check. So, use diagrams to show how the following ionic compounds are formed. Ionic is when it's a metal and a non-metal. Metals want to lose electrons and non-metals want to gain electrons, because metals are close to being empty on the outer shell and non-metals are close to being full on the outer shell. So magnesium is Mg12. So it wants to lose 2 electrons. It's in group 2. And Cl is in group 7. 17, but we will call it 7. There's 7A there. And it wants to gain 1 electron. So it's MgCl2. So we want to draw the formation of them. So we need to draw the atoms to start off with. Mg, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and Cl17, Cl 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There's 2 of those. And the electrons from magnesium will go to the chlorines. And when that happens, magnesium will become an Mg2 plus ion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mg2 plus, and Cl will become a single minus ion. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, because it's got that many. Because it's got that many electrons, it's going to be 1 extra negative than it should be. One minus, and those 2 1 minuses balance out the 2 plus of the magnesium. Magnesium chloride done. Lithium oxide. Lithium group 1. Here it's 3 oxide, group 6, 8. Lithium, Li, 1, 2, 3. Li2, forgot what oxygen was already. It was 8 and it was in group 6, so it wants to gain 2 electrons. O, 1, 2, 3, 4, 5, 6, 7, 8. Lithium's going to donate an electron each. I forgot to draw the arrow here. So that becomes Li 2 electrons. So it's going to be 1 plus. There's going to be 2 of those. That looks like a H. 1 plus, there will be 2 of those. And oxygen will have 2 extra electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore will be 2 negative. And those 2 negatives balance out the 2 1+s of the lithiums. Lithium oxide, done. Use diagrams to show how the covalent compounds are formed. Dihydrogen monoxide, otherwise known as water. I know these off the top of my head. H is 1 negative, there's 2 of them. Oxygen has 6 on the outer shell. 2, 3, 4, 5, 6. Now we want to show the covalent bonds forming. So oxygen, hydrogen on either side. The areas of electron sharing. Hydrogen has 1 to give. The other hydrogen has 1 to give. And oxygen has 1. It's sharing 1 with each hydrogen, and then it's got the 6 remaining in the outer the 4 remaining in the outer shell. So 1, 2, 3, 4. 1, 2, 3, 4. So 6, but these electrons aren't going to be across from each other. Water is a bent molecule, so it's going to be more like this. H, H. And so now I can do the change the pairs of electrons into lines. So I'll clean this up a little bit. I don't actually need, I should have started with the original working out. So you're going to finish with ... water. Methane. Carbon has 4 on the outer shell. It's bonding with, haven't given myself enough room here. H, 1, 2, 3, 4. Hydrogens each have 1 electron to share. Carbon has 1, 2, 3, 4 on the outer shell. So I should have drawn an arrow there as well. It's going to be C, H, 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 and H. Methane. Write chemical formulae for the following substances. So we practiced these in class. You will have ion charts, but this isn't applicable here except for these. Prefixes, just to remind yourself. Sulfur trioxide, SO3, dinitrogen pentoxide, N2O5, phosphorus trichloride, Cl3, dihydrogen monoxide, H2O. Name the following compounds: carbon dioxide, 2 nitrogens, dinitrogen, 4 tetroxide, sulfur, 6 hexa fluoride, P, how do I spell that? Phosphorus, pentachloride. Balance the following chemical equations. You do not need to indicate the states of the reactants and products. You're just balancing. So all you're messing around with is the numbers in front of the substances. You cannot change the small number because that would change the substance. 2 H's, 2 H's, 2 O's, 1 O. So the immediate fix is putting a 2 in front of this. Now I'll have 2 O's, which fixes the oxygens. But now I have 4 hydrogens, which I can fix by putting a 2 in front of H2. That's that one done. Sodium hydroxide, sulfuric acid, sodium sulfate, I think that is, and water. Sodium, 2 sodiums. Double that. Oxygen, 2 oxygens, 2, 3, 4, 5, 6. So there's 2 from there and 4, 6. We have 4 and 1. So I can correct that by doing 2 there. That messes up hydrogen. We have, how many hydrogens? There's 2. Double this, 2, 3, 4. There's 4. How many S's do we have? 1 and 1. How many oxygens do we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's balance. This one looks tricky. C6, correct the C's. C6, 6 there. H12, 12, 2. Now there's 12 on the right hand side. O6, 6, 7, 8. 6. We've got 8 on the left hand side. Here we have 6 times 2, 12. 18. I have 18 on the right hand side. I don't want to mess with this anymore. So there's 6 oxygens used up in the 18 that I want here. So 18 minus 6 is 12. I need 12 oxygens. How would I get that? By multiplying that by 6. Let's check. C6, 6 C's, H12. H2 times 6 is 12. 6 oxygens plus 12 oxygens, 18 oxygens. 6 times 2, 12 plus 6, 18. Done. I'll leave that for working, but you don't need that. I'll just cross it out. Determine the molar mass of the following compounds. So, carbon and hydrogen. You'll have a periodic table with molar masses. Carbon 12.01, hydrogen 1.01. 1.01. Molar mass is going to be 12.01 plus 4 times 1.01. 4 times 1.01 plus 12.01. 16.05. Mass in grams. CaCO3. Ca, I don't know that off the top of my head. Let's check. Calcium 40. 40.08. 40.08. Carbon we already got. 12.01. Oxygen. Oxygen 15.99. That's going to be 16 exact. Molar mass 40.08 plus 12.01 plus 3 times 16 equals 40.08 plus 12.01 plus 3 times 16, 100.09. 100.09 grams in 1 mole of CaCO3. C6H12O6, carbon was 12.01, hydrogen was, I wrote O there, H was 1.01, O was 16, so molar mass 6 times 12.01 plus 12 times 1.01 plus 6 times 16. Need to liberal use of brackets here. 6 times 12.01 plus 12 times 1.01 plus 6 times 16. 180.18 grams. Calculate the number of moles in 24 grams of carbon dioxide. So C is equal to N on V. That's the wrong formula. N is equal to the number of grams over the molar mass. I need to know the molar mass of carbon dioxide. M is going to be 12.01 plus 2 times 16. 12.01 plus 2 times 16. 44.01. grams. Writing's terrible. A bit sleepy. Number of moles, N. I have 24 grams of carbon dioxide over the molar mass of carbon dioxide, which is 44.01 grams. So N is going to be 24 divided by 44.01, 0.55 moles to 2 decimal points. A sample contains 0.2 moles of hydrogen gas. What is the mass of the sample? Number of moles is equal to the mass over the molar mass. Molar mass of hydrogen gas is going to be 2 times by 1.01, which is going to be 2.02 grams. 0.2 moles is equal to unknown mass over 2.02. The opposite of dividing by 2.02 is timesing by 2.02. Move this into the middle. That cancels out. 2.02 times by 0.2. Mass is going to be 0.40, rounded to 2 decimal points, grams. Put the rounding indicator in the wrong place. .4 grams. That's that. A sample contains 0.75 moles of ethanol. What is the mass of the sample? Number of moles is equal to the mass over the molar mass. This is a tougher molar mass, is equal to 2 times by, carbon was 12.01, plus 5 times, I'm going to bracket these, plus 5 times by 1.01, plus 16 plus 1.01. Put the calculator on the other side, it's getting in the way. 2 times 12.01 plus 5 times 1.01 plus 16 plus 1.01, 46.08 grams. For a mole of ethanol, sample contains 0.75 moles. 0.75 is equal to the unknown mass over 46.08 times by 46.08 is the opposite of dividing by 46.08. And to balance it out, I need to times by the same thing on the other side. 46.08 cancels. 46.08 times by 0.75, 34.56, so the mass is equal to 34.56 grams. What do we have? Find the concentration of a solution with 0.5 moles of sodium chloride in 2 liters of water. Concentration is the number of moles over the volume. He's got concentration is equal to number of moles, 0.5 over the volume, 2. Concentration is going to be 0.25 moles per litre, or 0.25 m. I'm going to use the big M from now, 0.25 molar, just quicker. How many litres of solution will we need to achieve a concentration of 0.267 molar containing 0.4 moles of magnesium chloride? Concentration is number of moles over the volume. How many litres? We want a concentration of 0.267 equals the number of moles is 0.4 over the volume. The opposite of dividing by V is timesing by V. I need a times by V on both sides. Those V's cancel out. So I'm left with V times by 0.267 is equal to 0.4. I want what V is, so I need to get rid of this timesing by 0.267. So the opposite of that is dividing by 0.267. I need to do the same thing on both sides. Those cancel out. So volume is equal to 0.4 divided by 0.267, 1.50, 1.50 litres rounded to 2 decimal points. How many moles of C6H12O6 would be needed to make a 1.2 litre solution with a concentration of 0.75? Concentration is number of moles over the volume. 0.75 is the concentration. Number of moles is unknown. Volume is 1.2. Opposite of dividing by 1.2 is timesing by 1.2. I need to do the same thing on both sides. Cancels. N is going to be 1.2 times by 0.75, 0.9 moles. You have 500 milliliters of a 2 molar hydrochloric acid solution. How much water should you add to dilute it to 1 molar? C1V1 equals C2V2. Concentration 1 is 2. times by the volume of 500 mils is 0.5. Concentration 2 that I want is 1 molar times by unknown volume. 2 times 0.5 is 1. 1 times by V2. Opposite of timesing by 1 is dividing by 1. Divide both sides by 1. That cancels. V2 is going to be 1 divided by 1. V2 is going to be 1 litre. So that's what we want the volume at the end to be. We started off with 500, therefore need to add 500 millilitres to make up 1 litre. Okay, that's that question done. How much 3 molar H2SO4 is needed to make 600 millilitres of 1 molar H2SO4? C1 V1 equals C2 V2. I know the original concentration. I don't know how much of it there is. I want 1 molar afterwards, and I need to make 600 mil, 0.6. 3 times V1 is equal to 1 lot of 0.6. Opposite of timesing by 3 is dividing by 3. Cancels. V1 is going to be, my calculator's on the other side, 0.6 divided by 3, 0.2 litres, therefore 200 millilitres of 3M H2SO4 is needed. Next question. To prepare 400 millilitres of 0.2 molar sodium chloride solution from a 2 molar stock solution, how much stock solution do I need? C1 V1 equals C2 V2. I have a 2 molar stock solution that I'm starting with, times by, I don't know how much stock solution, so V1 equals concentration 2. I want it to be 0.2 molar times by the volume 2, 400 mils, 0.4. 0.2 times by 0.4, 0.08 is equal to 2 times V1. Opposite of timesing by 2 is dividing by 2. That cancels out. So V1 is going to be 0.08 divided by 2, which is 0.04 litres. Therefore, 1, 2, 3, 40 millilitres of stock solution needed. Using the concept of electronegativity, explain the difference between a polar and a non-polar bond. You may use an example or diagram if needed. The best way we need to do this is to look at the periodic table. The most electronegative, the most strongest pull of electrons is F, fluorine, and the least pull, the most electropositive, is this. So as they get closer to fluorine, going diagonally up, more more electronegative. So it pulls the electrons more towards that side, or that atom in the covalent bond where they're sharing electrons. So a polar bond and a non-polar bond. Let's do the non-polar first. Non-polar bonds are those in which the two atoms have the same electronegativity, so the shared electrons in the bond are pulled by the atoms equally. So the electrons would be in a region in the middle, e.g. there'd be a cloud of electrons directly in the middle. Okay, but in polar bonds are those in which the two atoms have different levels of electronegativity. So the shared electrons in the bond are pulled closer to the more electronegative atom, so stay closer to it, causing there to be a dipole in the bond, i.e. a positive end and negative end of the bond. E.g. atom, let's say this is the more strongly electronegative one, this is the electropositive one. The electrons are going to hang out closer to this, and therefore in the bond between these two, I should have put a little circle around this to indicate that that's a bond. So that indicates that there will be a dipole here, and there will be more electropositive on this side and more positive on that side and more negative on this side, where the electrons are chilling out closer to the atom. Okay, so those are the differences between a polar and a non-polar bond. Move this up a little bit. Explain the difference between a polar and non-polar molecule. You may use an example or diagram if needed. So it's very closely related. These ideas are very closely related to polar and non-polar bonds. But now we are talking about the overall molecule, its shape, and the dipoles in the bonds being symmetrical. a non-polar molecule may have polar bonds, but their shape, orientation mean that the dipoles, this thing that we were talking about here, dipoles cancel each other out, so that overall there is not one end that is more positive and one end that is more negative. E.g. CO2. What does CO2 look like? C is in the middle. It has, well, it's got 4 electrons in the outer shell, so it wants to share those 4 in trying to get 8 on the outside. Oxygen has 6 on the outer shell. I think. Yep, 6 on the outer shell, so it wants 2 electrons shared with it. So it's going to form double bonds. But right now, oxygen is going to have 1, 2, 3, 4 shared with it. So it's going to have, and it's only sharing 2. It's only sharing 2 of its electrons in these bonds, because each of these lines represents 2. So where's the other 2 come from? Carbon. So oxygen is going to have 2 pairs of electrons left over on its outer shell, and the same with this other oxygen. So if we look back at the periodic table, oxygen is more electronegative than carbon dioxide. So there's going to be overall a pull or more negative side here. It's going to be more positive in the middle with carbon, but then you're going to have the same negative sort of charge on the other oxygen. So it's going to form a straight line here, and that pull is going to be exactly the same as that. That pole is going to be exactly the same as that pole there. So overall, it's going to be non-polar. Okay, there's no direction to the charge distribution. Whereas if you had a polar molecule will have polar bonds that result in the overall molecule having a dipole, which means that a certain area is more positive and another is more negative, e.g. water. We already drew a diagram of that up here. Oh, I shouldn't have duplicated. Copy biggest water I've ever seen. Hydrogen is very electropositive, so it's going to be more positively charged on those ends. And then you literally have a cloud of electrons on this side of oxygen, so it's going to be very negative on that side. Okay? There's no equal pull. These hydrogens aren't completely opposite each other. Why? Because these electrons are trying to push the electron clouds in these bonds as far away from each other. It's going to form like a bent shape there. All right, so that is explaining polar and nonpolar molecules. Using the diagram below and writing as needed, explain why ammonia is a polar molecule. Use the symbols to indicate the polarity of different regions in the molecule. It's not going to be symmetrical. First up, you're going to have these positive dipoles, positive regions here. It's going to be extremely negative there. The bonds with hydrogen are polar, so they are more positive towards the hydrogen atoms, and the two free electrons for nitrogen cause negative region at the top of the nitrogen atom. So there is a dipole in the molecule, so it is polar. Using the diagram below and writing as needed, explain why carbon tetrachloride is a non-polar molecule. Look back at the periodic table. Chlorine is going to be more electronegative than carbon. So it's going to be more positive towards the middle, and it's going to be more negative. These are all polar bonds. There's going to be 4 polar bonds there. Okay, but this tetrahedral shape is making sure that the chlorines in 3D space, remember this dotted line is going into the page. This arrow shape is showing that this chlorine is coming towards you. This is just like, what's the best word for it? It's like on the page, and this is on the page too. So this arrangement is the maximum distance that all of these chlorines can be from each other in 3D space. All right, so it's symmetrical, and they're all pulling with the same strength of dipole in all of the bonds. Okay, so chlorine is more electronegative than carbon, so the electrons in the bonds will be closer to the chlorines in the 4 polar bonds, but each dipole is equal, and they all pull with equal strength in balanced directions, so there is no overall dipole in the molecule, so it is non-polar. That's that question done. 25 milliliter, titration question. A 25 milliliter sample of phosphoric acid of unknown concentration is titrated with 0.1 molar sodium hydroxide, the equivalence point, so the color change is reached after 35.25 milliliters of sodium hydroxide. The balancing reaction is below. What's the concentration of H3PO4 solution? Show all working, you get credit for only working. We need to work out how many moles of sodium hydroxide there was in this 35.25 milliliters NaOH. Volume was 35.25 milliliters equals 0.03525 liters. Concentration was 0.1 molar. So, number of moles. Concentration is equal to N on V. Opposite of dividing by V is timesing by V. So, C times by V is equal to the number of moles. 0.1 times by 0.03525 is equal to the number of moles. The number of moles is going to be 0.1 times by 0.03525, 0.00525 moles. Zero 0.003525 moles. Now, the problem with that is that the ratio of sodium hydroxide to the phosphoric acid is 3:1. So this is 3 units of moles to 1 unit of this. So to work out the number of moles of phosphoric acid, I need to divide that by 3. So 0. Let's show the working. Ratio of H3PO4 to NaOH equals 1 to 3. So moles of H3PO4 equals 0.00525. Over 3. So moles of H3PO4 equals 0.00525 divided by 3, 0.001175. So now we can deal with H3PO4. Volume was 0.025 liters, 25 mils. Concentration is unknown, but we know the number of moles was this, So concentration is equal to 0.001175 divided by the volume, which was 0.025. So concentration is equal to 0.001175 divided by 0.025. Concentration is 0.047 molar. Okay. That is it, I believe. Yep. Hopefully that helps you out, and I'll see you in the next video.